Hello guys and welcome back. So let's keep on going with our setup. So two things I want to do. One is to get rid of this stretched effect. And also you can see, well, there's no perspective distortion here at all. Like this is also graphic view, right? We don't have any, this things doesn't get smaller when they're getting further away, right? And also probably better to push this back a bit. Okay, so let's go ahead and take a look at that. So basically we need two more matrices to do that, okay? We need one matrix to, kind of like move the model back. Okay. And we need another matrix to actually do the perspective projection. So let's do that. First thing I wanted to do is to make it go a bit farther, and that's just need another matrix to multiply with. Okay. So I'm gonna do a GLM matrix 4, and then I'm gonna call this view matrix. So I guess this shouldn't be called transform. It should be called matrix. Let me go ahead and change that. Cube trans, or I believe I call it model matrix. So the model matrix, and this is the view matrix. Okay, v equals to glm translate. We can just build something on site by translating a again an empty matrix, which is glm mat for 1.0. That's basically a empty matrix that doesn't do any transform. 0, 0, 0, right, for transform and rotation, and 1, 1 for scale. And then basically then we transform it with a vector 3. I'm going to move it backwards. And then, oh, actually, why am I moving that? I'm not gonna move it on x and y for the depths, -3.5. Okay. The camera is facing negative direction. So if you move an object that's -3 float number away, you're basically moving them away from the camera. Again, this is something we call the view matrix. It's the offset of where we want to move the camera. Again, the camera does not move. You move the objects to make it feel like the camera moves, right? So that's how it works. So we're gonna go ahead and create that uniform. Okay, so uniform mat for a view matrix. And we're going to apply that with another multiplication with our view matrix. Basically, a multiply with a matrix applies the transformation on the matrix to the the vector 4 you multiply with. So it's basically we're doing you read this backwards, so you move the model and you move it again here. So this goes first and this goes second, right? So you apply this transformation first, you apply the other one. This is basically how matrices work. If you want to know more about matrices, I highly encourage you to watch some one of the YouTube tutorials from 3D Brown, and he has a very graphic heavy tutorial on matrices and linear algebra. Very nicely done. I have learned a whole lot in there. Okay, and so basically for this, right, you just multiply it backwards. How do they multiply doesn't really concern you or us, right? This is just done internally. But all we have to know is what or how to use, what does those things represent, right? And how do we use them? They represent different things. They can represent rotation, transform, or a collection of rotation, transform, scale. And then we use those or apply that amount of transformation by multiplying it with a vector 4, right? That's going to move that over to after that transformation. Okay, so then we need to really pass it over, right? So we need to do a int view matrix location will be equals to gl get uniform location, right? We're gonna get it from our program, and then the name of the variable is called view matrix, right? And then we'll do the same thing, gl uniform 1 matrix for FV, right? And then we're gonna pass to our view matrix location, right? And then 1 and GL false, and then GLM value pointer, and then we're gonna pass in our view matrix. Okay. All right. Once we have that, this should be already passed over. So we'll see the model gets a little bit further away, but let's take a look. Okay, or maybe it's going way too far. So I'm gonna go change that to maybe 0.2 or something. Let's see how that looks like. Yeah, it's a little bit further away, maybe 0.4. Right, it's hard to tell yet, but you can see that clipping, right? So basically, am I moving it forward? 0.8. Let's see what we have. Yeah, we're actually moving it forward in this case. As you can see, this is getting clipping in. So I guess we have to also pass it through a a projection matrix to really see it having effect. So let's do that. Okay. So what we have to do is do another matrix, which is the projection matrix. This projection matrix defines how it looks like in the viewport by projecting the 3D thing through some calculations to get it looks like it has perspective and get it just views more naturally, and also it's gonna able to get us get the cube from stretching, right? It's already stretching horizontally too much. The reason is because we didn't tell it to be projected properly. So the matrix will actually be generated by GLM perspective function, right? We're going to tell it the degree. So GLM radians 45 degree, and then aspect ratio. We can calculate that real quick. Float aspect ratio will be equals to the float window width divided by float window height. Okay, and that's going to be the aspect ratio. And near and far clip plan near will be 0.01 f, and then far clip plan will be 100 something dot f. Anything beyond that number will be clipped out, right? Very typical to like a render viewport. Okay, and then again we need to then get the location, right? That's going to be another thing we call project mat location, which I haven't created that yet. So I'm going to go ahead and do that. It's called projection matrix, right? And then it's a uniform again. Mat4, right? Projection matrix will also be multiplied on top. Okay, alrighty. So that's gonna be equals to GL get uniform location one more time, getting it from our program, and then this time it's called projection matrix. Okay, alrighty. And then after that, we are gonna set it to GL uniform matrix for FV, right? And then view, this is gonna be our projection matrix location, and then size 1, not changing it. So GL false and GLM value pointer, and then we pass in our projection matrix. Okay, let's run this again. Now this time we're seeing something a bit different. We're seeing that, right? So I guess I'm moving it in a weird way. Let's not move it for now and see what we have. That actually will see, we probably will see more clipping. Yeah, we're seeing inside of the cube. That means it's projecting properly. Let's change that to -3. Yeah, that actually pushes away. So we needed to be using the projection matrix before we see the full effect. Now it fixes two things. One is that we can push it back by pushing it across the negative direction, right? And also we're able to get the correct aspect ratio, right? By basically having that passed in. And also this feels more like a cube now with perspective in there, right? That's all done by the projection matrix. Okay. Now with those multiplications, now we're able to see a very nice looking cube. Okay, so we can move ahead and have some more fun with it. So we can actually make this guy rotate. Okay, because we have the while loop, we can actually keep updating the cube model matrix, right? In this case, it's probably better to update that. If you wanted to, you know, change a few things, like everything we need to change, like perspective, right? Like the view matrix or the model matrix, we can actually get them all moved down there. So I guess we can cut them out and put it into the while loop. Right, put them in there, and then here we can actually define the rotation. Right, so I'm gonna do a float current previous time will be equals to GLFW get time. Okay, that will give us the current time. Okay, moving on from there, I'm gonna create another float, delta time. Okay, and we equals to 0. Okay, and then we can say, well, float current time will be equals to GLFW get time. Okay, and then delta time will be equals to current time minus previous time, and then previous time will be equals to current time again, right? That way we're able to get the time calculated properly. Actually, we can get it to get time, I believe. Yeah, so we calculate how much time that's different, and then we update the previous time, right? Shouldn't make much of a difference then, though, compared to make it equals to current time. Yeah, should be okay. So now after that, we have this delta time. That's basically the different time has passed, you know, between this frame and the next frame, basically, right? So then we can use that to be something we can add to our cube model matrix. So we're rotating it, right? But we're rotating it by that much. Okay, but now we can change that to rotating it based on the delta time times maybe a rotation speed. Rotate speed, okay, which is a variable I have to create. So I'm gonna go ahead and do that. Float maybe equals to 100 or something. Maybe 10. Let's not go too fast. Okay, so every time, right, we're gonna rotate it that much based on delta time, and our cube should be rotating. Let's take a look at that. Very small number. Don't see much, so let's try to make it go faster, maybe 1,000. It's actually rotating quite a lot. I think it's rotating, it's just maybe rotating too fast. Let me change that to 1.5 and see what we have. Not too much. 20. It's hard to see the difference. Oh yeah, because we started with 1, right? So we already defined that. Let's go ahead and we'll keep redefining it in this case. Let me move that before the while loop, right? That way we're not making it 0, which is rotated to add something. Right, that's it. So now you can see the cube is indeed rotating, right? and it's rotating across the axis with tiled. All right, very cool. So now we have the somewhat a working 3D engine, right? We can now load in different models. We can actually use some model loading libraries to actually loading third-party models built from Blender or Maya. And we can read a bunch of different things. But yeah, that's basically it for this video. Now we do have a rotating cube. Okay, I guess next thing we can do is to maybe set up some input so that maybe we can look around, right? Let's do that in the next video.